Okay, we want to go ahead and find this formula for the transform of a periodic function. So if f of t plus capital T being the period, equals f of t for all t from 0 to infinity, then what's the Laplace transform? Well, the Laplace transform we're going to say is equal to this. We want to prove it. How do we prove it? We write down the Laplace transform of f of t. There it is. Now we just break it into two integrals. One from 0 to t, and one from capital T to infinity. That's 0 to capital T, and capital T to infinity. Now this integral is just the integral of f of t e to the negative ts, but shifted t units to the right. Okay, it's the integral of, it's this integral shifted t units to the right. If you look at it geometrically, you have the graph of f of t from 0 to infinity, whatever that graph might look like, integrated against e to the negative ts. Here you have the part of the graph from capital T to infinity. Since the graph repeats with period t, then all we're doing is integrating over everything but the first period. If we were to shift this graph, capital T units to the right, we would have this. Okay, so this is the integral from 0 to capital T, f of t e to the negative ts dt, which is of course going to be our numerator here, plus the integral from 0 to infinity of f of little t plus capital T, because of course when you replace t by t plus capital T, you shift the graph capital T units to the left. And we also of course replace this t with a little t plus capital T. Okay, well now this equals the integral from 0, almost wrote it, not almost, I started to write infinity, and I got to correct that. Okay, from 0 to capital T of f of t e to the negative ts dt plus, well, we can split this e to the negative t plus capital T times s into e to the negative ts times e to the negative capital Ts. Yeah, I better write that in two steps. Okay, just to make sure that we're clear, this is 0 to infinity, little f of t plus capital T. And I'm going to write this as e to the negative capital Ts times e to the negative little ts dt. Now e to the capital Ts, or negative capital Ts, is just a constant. It has no time dependence, has no little t dependence. So this is then going to be the integral from 0 to capital T of little f of t e to the negative ts plus e to the negative capital Ts times the integral from 0 to infinity of f of t plus capital T e to the negative ts dt. So now we've got our e to the negative capital Ts out here. It's going to end up here. I'm going to see why. f of t plus capital T is just equal to f of t. Okay, you're just integrating this thing from 0 to infinity over all periods of the function. So it doesn't matter if you call this f of t or f of t plus capital T. So what we have then is the integral from 0 to capital T of little f of t e to the negative ts dt. Left out my dt here. Okay? Almost wrote my t plus capital T, and I want to get rid of that smudge. Smudges often obscure things when you get to the video. Okay, now might not seem like we've made a lot of progress here. Let's make sure things are getting a little crowded down here. Okay. This integral is just a Laplace transform of f of t. This integral is the same as this one. So we conclude, see how much room we've got here, that the Laplace transform of f of t, which is what we started with here, is the integral from 0 to capital T of little f of t here plus e to the negative capital Ts times the Laplace transform. Okay, well, now we can rewrite this. If we subtract this from both sides, we get Laplace transform of f of t times 1 minus e to the negative capital Ts equals our integral from 0 capital T of f of t e to the negative ts dt. And now we get our theorem, because we divide both sides by the 1 minus e to the capital Ts. And there we have it. And we've proven what we set out to prove. It's actually very simple. All you have to understand is how you translate a function in the horizontal direction to get from here to here, and then how you split the exponential apart here. This part comes out of the integral, and then f of t plus capital T always equals f of t, so we get this. Now there's 3 ideas there, but they're all very simple ideas. To get from this to this is just simple algebra. Replacing this by this, it takes a little attention to the condition of periodicity, and bringing this out of the integral just requires that you recognize that this has no dependence on the variable of integration, so it's a constant. It can come out of the integral. Then we just rearrange it, and there we have it. Now there's not a whole lot of insight into what this means geometrically, and we're going to want to talk about that. But there's the theorem and it's very, very handy.